So today we're lucky to have Denis Oriot, who's a pediatrician and anesthesiologist with 20 years of experience in pediatric intensive care and emergency medicine. Denis is one of the pioneers of simulation-based training in France. He completed his fellowship at McGill University, where he learned about simulation. And in addition to his medical degrees, he also has a master's in science and neuroscience and a PhD in ethics. His areas of interest include evaluation, stress, teamwork, debriefing, and breaking bad news. And he's currently responsible for the simulation laboratory in Poitiers, France. We're very lucky to have him talk today on how to build and validate a performance assessment scale. So with that, I'll hand it over to you, Denis.
Hello, everybody. Can you hear me? Can you hear me? Okay. So I would like to thank first the organizing committee of INSPIRE Network, and especially Taylor, Mark, and Cathy for their invitation for today's presentation and their help to fix the presentation. In the simulation laboratory in Poitiers, France, we have developed some interest for evaluation tools. And today I will talk about procedural assessment in technical skills as an example. But the principles of validation process for a performance assessment scale can be applied to any type of practice in simulation. At the end of this workshop, you will be able to plan a strategy for building a performance assessment scale, understand the validity reliability dilemma and its statistical tools, and design a simulation sessions for validation steps. First, in simulation-based training, there is a great need for evaluation tools able to provide valid and reliable assessments. A recent work by Cook from the Mayo Clinic Office of Education Research showed that out of 417 original research studies evaluating the validity of simulation-based assessment scales, only 52% reported more than one element of evidence, and among those, only 6 studies used the complete 5-source framework for evidence of validity. So tools are needed, but for what purposes? To assess not only results of actions, but also processes. Validity will include building a validation of the evaluation tool, how well the design tool does the job. It is crucial to move our view from the success rate of the procedure to the process of the actions involved, because success depends on the quality of the performance, the process, and the training phase requires detailing of all the procedural manual skills required to reach success. We have had the opportunity to study in detail the process of intraosseous needle insertion and have validated a performance assessment scale published 2 years ago in Simulation in Healthcare. We should aim at assessing what leads to success and not just success itself. Of course, the mental frame for a specific action is invisible, unobservable, and unknown. By contrast, the process is observable and measurable, but because there does not exist a strict bijection between process and success, it is also important to assess success rate. Now, what is the validation process for such an assessment tool? First, it is not the validation process of the tool itself, but rather of the of the interpretations and uses to which the scores produced by the tool are put. Second, it is a question of validity and reliability. You all know this picture characterizing what is the validity of a test, aiming at the center of the target, and what is its reliability, having close shots. But what you may not yet be aware of is the validity-reliability dilemma when considering an assessment scale. The more closely the assessment tool reproduces reality, the more valid it is. But paradoxically, it is less reliable because it includes a lot of details that are less reproducible between two blinded observers. By contrast, the simpler is the tool, the better its reproducibility. But unfortunately, it loses validity because too many simplifications were made in order to copy reality. So the aim is the validation process of a performance assessment scale. It should be understood as providing evidence for validity, and construct validity represents the whole of validity from a scientific point of view. The unified model of validity is currently represented by the 5 source frameworks published by Dunning in 2003. It is an argument-based approach using 5 different sources of evidence. 1, content, involving the elaboration of the scale. 2, response process, implying modifications of the pre-scale. 3, internal structure, including approaches to both validity and reliability. 4, relationships to other variables aimed at validity alone. And 5, consequences, which represents the utility of the scale. We will consider each of these 5 steps. First, the content. It means domain, relevance, and representativeness of the scale. It should be totally included within the domain and not cross its borders. That means that all the items of the scale must deal with the procedure they are supposed to represent. But even so, there can be a lack in fidelity, validity of the scale, if the chosen items represent only a small part of the domain. Then there is an obligation to determine and pick up significant items, the most representative, of the procedure. How is it possible and advisable to collect and revise the content of a scale? One can use the Delfy method, but it requires time, and at the end, you may not get what you are expected to get. A list of objectives items. The nominal group technique is quicker, but you can also go along with expert opinions only, because a small group of experts may be more aware of all the requirements of the scale according to the uses you have planned for it. And of course, the quality and quantity of items may change depending on the goal, the field of assessment, the target population, the type of instrument you use, and the implementation program to which you intend to apply the scale. One big issue will be the way you formulate the verbatim of the description of the actions of a procedure. A checklist is a scale with yes-no questions, which in many cases can include subjective interrogations like this one. Correct insertion of the intraosseous needle? Yes, no. What does correct mean? It may not mean the same for everybody. This possibility will lead to a decrease in reproducibility of the scale because subjective items first increase the variability of answers and then decrease their reliability. This drawback can be partially overcome by introducing a 3 or more points Likert scale for the answer. This is more accurate, but still some subjective propositions like correctly, incorrectly will introduce a decrease in reliability. The best option is to provide a more accurate factual description of the action, such as the one we chose for our I/O performance assessment scale. One item was described like this: I/O insertion technique, absence of twisting motion or mild twisting motion, or 1 or 2 moves or non-actual insertion, and finally actual twisting motion. By increasing description, you will increase the reliability of the scale. At the end of the first step, you will obtain a pre-scale or pre-checklist comprising items extracted from the literature or previous sources. Before being run on trainees, however, it requires a close rereading to avoid ambiguities and to ensure the clearest written expression of what is supposed to be assessed. Second step of the validation process of the scale, the response process. The aim of this step is to control all possible sources of errors, which implies making changes of the content and/or writing of the items of the prescale. To do so, the prescale should be run on a proficient population, at least 10 persons, who will be used as guinea pigs. To reinforce this step, you can already involve 2 blinded observers and use their discordances as sources of improvement of the prescale. Then you may modify the items of the scale because of redundancy, too much complexity, lack in accuracy, etc., or the way you conducted the briefing of the fake trainees and/or the ranking system you established. These modifications must be carried out by a step-by-step approach, aiming for at least 80% concordance between 2 blinded observers. At the end of the second step of the validation process, you end up with a final scale, which has been modified from the prescale according to the prescale scoring, by combining items, deleting, or formulating some of them in a more accurate way. The third step of the validation process is a truly major step. It involves 3 statistical analyzers: internal consistency, reliability, and generalizability. At this stage of the validation process, you should consider recruiting a mixed population of trainees, both novices and experienced ones, between 15 and 30 participants who are not considered as guinea pigs. Internal consistency of the scale means the pertinence of the chosen items to describe the process without redundancy. It can be evaluated by calculation of the value of the Cronbach alpha coefficient. It is commonly accepted that this value should be between 0.7 and 0.9. Below 0.7 means that the chosen items are not sufficiently linked to each other. Above 0.9 means that some of the items are redundant. For this reason, search of redundancy between items, it is important to calculate the Cronbach alpha for each section of the scale. If it appears that redundancy exists in a given section, it should lead to a modification of the scale in order to prevent it. Reproducibility is the best way to assess reliability. Its statistical analysis relies upon a comparison between two assessments. When involving a rater at two different times, it is the test-retest of intra-observer reproducibility, but there might be also a time effect to be considered. When involving two independent blinded raters at the same time, it is inter-rater reproducibility. Statistics commonly use the kappa coefficient if it is a qualitative variable and the intraclass coefficient for a quantitative variable. In both cases, it is desirable to have a coefficient above 0.7. The higher the coefficient, the more reproducible the scale. You can also carry out a linear regression and calculate the equation of the line, aiming for a R-square factor above 0.5. As for the Cronbach alpha, it is interesting to calculate the ICC for each section of the scale. If it happens to be below 0.7, it could lead to further modifications of the scale aimed at improving reproducibility. You can see here an example of the expression of the results of reproducibility analysis with the linear regression between the scores given by observer 1 and observer 2 compared to the identity line and the results for kappa and ICC, which were very high in our intraosseous performance assessment scale. But there is also another expression I like, even if you do not always publish such a graph. It is to plot the results of observer 1 and 2 along the whole group of participants. Here is an example of this representation we obtained with our performance assessment scale for chest tube insertion in traumatic pneumothorax, in blue observer 1 and in red observer 2. They are almost identical. Finally, generalizability is the third statistical analysis of the internal structure step of the validation process. It is rooted on the variance of the standard error measurement. One approach can be the comparison firstly between each observer for the means, t-test, and the standard deviation, f-test, and secondly, each of the observers with the mean value of observer 1 and 2 for the means and the standard deviations. Obtaining non-significant difference is a further guarantee of the generalizability of the scale. The fourth step of the validation process of the scale is relationship to other variables. It is aimed at studying the pertinence of the studied procedure to evaluation. It is specifically related to scale validity. The overall score of the procedural scale should correlate with other established evaluation methods. Comparisons should be carried out within each participant to a gold standard, such as success assessment of the procedure or any other performance assessments, or between different subgroups of your population of participants, like novices versus experienced ones. When readying yourself for this step, it is important before starting the validation process, one, to make sure that the criteria of success of the procedure are strictly defined and will also be assessed by the observers. Two, to include both novices and experienced participants in your recruitment. For example, here you can see the distribution of scores obtained from the performance assessment scale of chest tube insertion, nicely splitting into two populations of participants according to the success rate. This is an example of contrasting groups method where process, the score of the scale, is strongly linked to success. You can even go further with mathematical calculating pertaining of the cutoff score. Finally, the last step of the validation process is consequences. It is a description of the consequences on examinees as well as those on teaching and learning. It includes several questions that require answers. Is the evaluation to be performed during a formative or summative assessment? Is there a cutoff score? If so, what is the passing rate? What is the standard error of measurement at pass score? What is the reliability between observers of the pass-fail decision? What are the consequences of a failing score? What type of feedback is given after the score? And finally, did evaluation modify training? For example, you may have chosen an arbitrary cutoff score of 10/20, as we did for our chest tube insertion performance assessment scale, which appeared to be too low because it did not guarantee full success compared to 13 and especially 14/20. So you can calculate what would be the score with the best PPV and NPV for success and adapt your training evaluation correspondingly. In conclusion, there is a great need for evaluation tools in simulation-based training and therefore a great deal of room for research in development of validated new tools. To do so, it is mandatory to remember that one should follow the 5-step framework from Denis, paying particular attention to the content step, from which everything else is derived. Validation of an assessment scale requires using two types of participant populations, and this should be clearly anticipated. One population of proficient participants for adjustments of the scale during the response process step, and one mixed population, novices and experienced participants, for the other step of the validation process of the scale.